Hi there. In this interview, we are going to walk through some of the hardest incidents you will ever face in production. Not simple CPU spikes, not obvious misconfigurations. I am talking about the kind of incidents that wake up executives, confuse dashboards, and force you to make decisions with incomplete information. This is designed to feel like a real interview. I will ask the question. I want you to pause the video and answer out loud before you listen to the sample response. Treat it like a real panel. No notes, no Googling. If you find this useful, subscribe so you do not miss the next interview in this series. Let's begin. Warm-up behavioral questions. First question. Tell me about the most stressful production incident you have handled. What made it stressful, and how did you operate under pressure? Pause here and answer out loud. A strong candidate might say, "The most stressful incident I handled was a payment outage during peak traffic. What made it stressful was not just the technical impact, but the business impact. Revenue was directly affected, support tickets were flooding in, and leadership joined the bridge within minutes. The first thing I did was slow myself down. I explicitly stated what we knew and what we did not know. I assigned someone to own communication updates every 10 minutes, so I could focus on investigation. Technically, I started by checking recent changes, deployment history, and error rate metrics. At the same time, I made sure we had someone validating impact from the customer side. What helped most was staying structured. Even under pressure, I followed a mental checklist. Recent changes, infrastructure health, downstream dependencies. We identified a misconfigured feature flag interacting with a cache layer. We rolled back the flag first to stabilize users, then investigated root cause later. The stress was real, but structure kept it manageable. Second question. Describe a time when the root cause of an incident was not obvious. How did you approach the ambiguity? Pause and answer. A strong candidate might respond, "I treat ambiguous incidents like hypothesis testing. Instead of chasing random signals, I define possible failure domains. Application layer, infrastructure layer, network layer, external dependency, then I try to eliminate entire domains quickly." In one case, latency increased across multiple services, but CPU and memory were normal. That ruled out obvious resource exhaustion. We checked database performance and saw no major locks or slow queries. That narrowed it further. Eventually, we discovered a networking issue between availability zones that did not show up as a hard failure, just increased packet retries. The key was not jumping to conclusions. I stayed disciplined about isolating layers instead of reacting emotionally to noisy metrics. Third question. Have you ever made a mistake during an incident? What did you learn? Pause and answer. A strong candidate might say, yes. Early in my career, I once restarted multiple services at once during an incident because I suspected a memory leak. That created a cascading restart effect and actually increased downtime. What I learned is that during incidents, changes are risk multipliers. Every action should be deliberate and minimal. Now I follow a principle of smallest possible stabilizing action. Instead of broad restarts, I isolate one instance, test impact, and observe before proceeding. I also communicate clearly before making disruptive changes, so everyone understands the risk. Incidents taught me humility. You can fix the wrong thing very quickly if you are not careful. Core technical and scenario questions. Let's move into technical depth. First scenario. You are on call. Suddenly, error rates spike across multiple services. Dashboards show red everywhere. However, infrastructure metrics look healthy. No obvious CPU spikes, no memory pressure. Where do you start? Pause and answer. A strong candidate might think out loud like this. If everything is red at the same time, I suspect a shared dependency or control plane component rather than isolated service failures. When multiple services fail simultaneously, it often points to something central. I would first check shared systems, authentication providers, databases, message queues, service mesh or ingress controllers, even DNS. I would look at request patterns. Are failures uniform or tied to specific endpoints? If all services that depend on a particular internal API are failing, that is a signal. I would also check for configuration changes, feature flags, certificate expirations, secrets rotation. These often do not show up as CPU issues, but can break everything logically. The key is to look for common denominators, not individual symptoms. Next question. Imagine you are dealing with a cascading failure. One service slows down, which causes retries from upstream services, which overloads the system further. How do you break the cycle? Pause and answer. A strong candidate might respond, cascading failures are about feedback loops. The first step is to reduce amplification. Retries, aggressive timeouts, and unbounded queues are usually the accelerants. I would immediately consider reducing retry rates or temporarily disabling non-critical traffic. If we have circuit breakers, I would check whether they are tripping correctly. If not, I might manually limit traffic at the ingress layer to protect the core system. Sometimes, the fastest stabilization is to shed load, return partial responses, disable non-essential features, protect the most critical transaction path. You do not try to fix everything at once. You stabilize the blast radius first. Once pressure drops, you can address root cause safely. Next scenario. You deploy a change that passes all automated tests. Within minutes, production latency increases dramatically, but only for a subset of users. How do you reason about that? Pause and answer. A strong candidate might say, subset impact tells me this is likely related to data shape, geography, or feature targeting. I would check whether this release included feature flags targeting specific user segments. I would compare logs or traces between healthy and impacted requests. What is different? Are certain database queries triggered only for premium users? Is there a regional cache miss pattern? I would also examine whether the deployment changed resource allocation patterns, like thread pools or connection pools, that only surface under specific workloads. The mindset here is differential analysis. What is true for impacted users that is not true for healthy ones? Final question for this section. What makes certain incidents truly hard compared to routine outages? Pause and answer. A strong candidate might respond, the hardest incidents are not about obvious failures. They are about silent degradations, partial failures, or misleading signals. When metrics say healthy but users are unhappy, that is hard. When multiple small issues interact in unexpected ways, that is hard. They are hard because uncertainty is high and information is incomplete. You have to make decisions without perfect visibility. You balance speed against risk. You decide whether to roll back, throttle traffic, or wait for more data. The technical complexity matters, but what really makes them hard is the need for judgment under pressure. That is where experience shows. We will continue deeper from here. Let's continue going deeper. Next scenario. You are in the middle of a severe incident. Latency is high. Error rates are rising. You suspect the database is involved, but database metrics look mostly normal. No obvious CPU saturation. No disk pressure. What do you do next? Pause and answer. A strong candidate might think through it like this. If the database looks normal at a resource level, but application latency is high, I start thinking about contention, locking, or query patterns rather than infrastructure limits. First, I would look at slow query logs or query performance dashboards. Sometimes average CPU hides the fact that a small number of queries are blocking others. I would check for long-running transactions, lock waits, or sudden changes in query plans. I would also correlate this with deployment history. Did we introduce a new query path? Did an index get dropped or become ineffective due to data growth? If metrics are still inconclusive, I might take a targeted approach. Capture traces for slow requests and inspect where time is being spent. Is it waiting on the database? On connection pool acquisition? On network round trips? The key insight here is that not all database incidents show up as obvious resource spikes. Logical contention and inefficient queries can degrade performance without maxing out CPU. Now, another scenario. Imagine you are facing a multi-region outage. Region A is down completely. Traffic is failing over to Region B, but Region B starts degrading under the sudden load. What are your priorities? Pause and answer. A strong candidate might respond like this. First priority is stabilization, not perfection. If Region B cannot handle full global traffic, we need to decide how to shed load intelligently. I would check auto-scaling limits immediately. Are we capped by quotas? Are scaling policies too conservative? If scaling can buy us time, that is the least disruptive move. If scaling is insufficient, I would consider traffic shaping. That could mean rate limiting non-critical endpoints or disabling certain heavy features temporarily. Protect the most important user journeys first. At the same time, I would assess the blast radius of Region A. Is it a network partition, a cloud provider issue, a bad deployment? If it is a deployment, rollback might restore capacity faster than scaling Region B endlessly. There is a trade-off here. Aggressively scaling Region B increases cost and may still not stabilize if a shared dependency is failing. You have to validate whether the failover architecture itself is healthy. This is where architecture design shows up during incidents. Multi-region redundancy only works if each region can truly operate independently. Next question. You suspect a memory leak in a long-running service, but restarting it would cause a brief but visible outage. How do you approach this? Pause and answer. A strong candidate might think out loud. First, I want to confirm whether it is truly a leak or just memory pressure due to traffic. I would look at memory usage over time. Is it steadily increasing regardless of load, or does it fluctuate? If it looks like a leak, I would check whether we have multiple instances behind a load balancer. If so, I can restart instances one by one in a rolling fashion to minimize impact. If we only have a single instance, then the problem is architectural. In that case, I would weigh the cost of a controlled brief outage now versus a potential uncontrolled crash later. Often a controlled restart during a communicated maintenance window is safer than waiting for a sudden failure. I would also start capturing heap dumps or profiling data before restart if possible. Incidents are opportunities to collect forensic evidence. If you just restart without capturing anything, you lose the chance to diagnose root cause. So the decision is not just restart or not. It is how to restart safely while gathering data for a permanent fix. Next scenario. You are told users are experiencing intermittent failures, but you cannot reproduce the issue internally. Logs show occasional timeouts between two internal services. Where do you look? Pause and answer. A strong candidate might say, intermittent failures often point to network instability, connection pool exhaustion, or resource contention under certain conditions. I would first check time correlation. Do timeouts cluster during traffic spikes? That suggests resource saturation. If not, it may be network jitter or DNS resolution issues. I would examine connection pool metrics. Are we exhausting available connections? Are threads blocked waiting for downstream responses? Tracing is particularly helpful here. Even if failures are rare, distributed traces can show patterns. Maybe only requests with large payloads fail. Maybe only requests routed to a specific instance fail. If internal reproduction fails, I would try to simulate production traffic shape more accurately. Production traffic often has edge cases that staging does not. Different payload sizes, different concurrency levels. This kind of issue is hard because it is probabilistic. You are chasing patterns, not deterministic failures. Final question in this section. How do you decide when to stop debugging live and instead mitigate and move investigation offline? Pause and answer. A strong candidate might respond, live debugging during an active incident is risky. Every diagnostic action in production carries some risk. So I try to separate stabilization from root cause analysis. If the system is unstable and users are impacted, priority is mitigation, rollback, scale, disable features, reduce load, get the system into a stable, predictable state. Once stabilized, I capture as much context as possible: logs, metrics, snapshots, traces, configuration state. Then deeper debugging can continue in a controlled environment. The moment to stop live debugging is when further probing could worsen the situation or when you have a viable mitigation that reduces user impact significantly. It is about discipline. Curiosity is good, but not at the expense of user experience during an active outage. We will now shift into higher pressure judgment scenarios. Now we are going to move into the hardest part of the interview. These questions are intentionally ambiguous. There is no perfect answer. What I'm evaluating here is how you think under pressure, how you prioritize, and how you manage risk when information is incomplete. First scenario. You are the incident commander during a major outage. Executives are asking for updates every 5 minutes. Engineers are trying to debug. The root cause is unclear. Tension is rising in the call. What do? Pause and answer. A strong candidate might respond like this. In that situation, clarity of roles becomes critical. I would explicitly separate communication from technical investigation. If I am incident commander, I would assign a dedicated communications lead. That person handles executive updates and stakeholder messaging. Engineers should not be interrupted every 5 minutes to answer status questions. I would also set a predictable update cadence. For example, updates every 15 minutes unless there is a significant change. That creates psychological stability. Stakeholders know when to expect information. Inside the technical channel, I would enforce structure. One person speaking at a time. Hypotheses stated clearly. Evidence shared explicitly. Incidents become chaotic when everyone talks over each other and jumps to conclusions. If root cause is unclear, I would encourage parallel hypothesis testing rather than deep diving one path blindly. But I would limit it to a few clear tracks so we do not fragment attention. Most importantly, I would protect the engineers from pressure as much as possible. Fear and stress degrade cognitive performance. The commander absorbs the pressure so the team can think clearly. Next scenario. You discover that the outage was caused by a configuration change made by a junior engineer. It was an honest mistake. The impact was significant and visible to customers. Leadership is upset. How do you handle this? Pause and answer. A strong candidate might say, first, I would frame the situation as a systems failure, not an individual failure. The fact that one person could cause that level of impact means our safeguards were insufficient. Did we have peer review? Did we have automated validation? Did we have canary deployments? Did we have blast radius isolation? Blame feels emotionally satisfying in the moment, but it does not prevent recurrence. Process and guardrails do. Privately, I would support the engineer. Incidents can be psychologically heavy, especially early in someone's career. The worst outcome is losing a capable engineer because they are afraid to touch production again. In the post-mortem, I would focus on control gaps. For example, why was the configuration allowed to reach production without validation? What systemic improvement can we make? Mature organizations treat incidents as tuition for resilience. That mindset protects culture long-term. Next scenario. You are unsure whether to roll back or apply a forward fix. The system is unstable but partially functional. Rolling back will restore stability, but reintroduce a known security vulnerability. What do? Pause and answer. A strong candidate might think through it this way. This is a trade-off between availability risk and security risk. I would assess immediacy and exploitability. Is the vulnerability actively being exploited? Is it theoretical or proven? What is the time window? If the outage is severely impacting users and revenue, and the vulnerability is low likelihood in the short term, a temporary rollback with compensating controls may be justified. For example, tightening network rules or limiting exposure. If the vulnerability is critical and actively exploitable, then rolling back may create a worse systemic risk than the outage itself. I would involve both security and engineering stakeholders in the decision. Document the risk assessment. Make the decision consciously, not reactively. The key here is transparency. Trade-offs are inevitable. Hidden trade-offs are dangerous. Final pressure scenario. It is 3 a.m. You have been awake for hours. The incident is mostly stabilized, but root cause is still unclear. The team is exhausted. Do you push to find root cause now, or do you defer until morning? Pause and answer. A strong candidate might respond, cognitive fatigue is real. After several hours, decision quality drops significantly. If the system is stable and no longer actively degrading, I would likely defer deep root cause analysis until the team is rested. However, before handing off, I would ensure that key data is captured, logs archived, metrics preserved, relevant dashboards snapshotted, context written down. There is a balance here. Some information is ephemeral. You do not want to lose it. But continuing to debug while exhausted increases the risk of mistakes. I would make a structured handoff plan, assign owners, define next investigation steps, schedule a follow-up. Resilience includes respecting human limits. We have covered a wide range of scenarios in this interview. Database contention without obvious resource saturation, multi-region degradation under failover, memory leaks with partial availability, intermittent timeouts that defy easy reproduction, leadership pressure during outages, cultural integrity after mistakes, security versus availability trade-offs, fatigue at 3 a.m. These are the kinds of incidents that define real careers. As you reflect on this session, ask yourself a few questions. Where did you feel most confident? Where did you hesitate? Which scenario forced you to slow down and think carefully? Those moments of hesitation are not weaknesses. They are signals. They show you where deeper understanding or experience will compound your effectiveness. If you are preparing for interviews, pause this video and try answering each question again out loud. Clarity improves with repetition. If you are already working in production environments, think about your current systems. How would they behave under these scenarios? Where are your blind spots? Let me know in the comments which question felt the hardest and why. Was it the security trade-off, the multi-region failover, the cultural challenge after a mistake? Your answer tells you something about your growth edge. If you found this realistic and helpful, subscribe so you do not miss the next simulation. Each session focuses on a different dimension of real-world DevOps pressure. The hardest incidents are not just technical, they are organizational, human, and strategic. And mastering them is what separates good engineers from great ones.